This video will cover section 9.5, the binomial theorem. The objectives for this lesson will be to use the binomial theorem to calculate binomial coefficients. Also, to use Pascal's triangle to calculate binomial coefficients. These two objectives are similar, but we can consider binomial theorem to be the long way and Pascal's triangle to be a very nice shortcut. The third and final objective will be to use binomial coefficients to write binomial expansions. And that's what we're going to do on the next slide. So a binomial, by definition, is a polynomial that contains two terms. So, for example, x plus y is considered to be a binomial. And for example, if we look at this term here, x squared plus 2x plus y squared, that will be considered a trinomial. And if it has more than three terms, we just call them polynomials. The way we can recognize how many terms are in the polynomial is by counting the terms that are separated by a plus or a minus sign. So what we're going to do is the different expansions of x plus y to a different power or exponent. So we're going to start with x plus y to the 0, and by definition, anything except for 0, so anything raised to the power 0 is equal to 1. So whether it's a variable, a monomial, or a number, or even a binomial, like the case that we have there. So it's just by definition equal to 1. The next example is x plus y to the power 1, so it will be enough to just remove the parentheses and the exponent, and it will just be x plus y again. For the next example, we have x plus y to the power 2, and so this will be x plus y multiplied by itself. So you have the x plus y binomial 2 times being multiplied. So the long way of multiplying this, if we distribute the x, it will be x times x, which will be x squared, then x times y, which will be xy, and then we will have y times x, which will be yx, and then y times y, which will be y squared. Now, it's important to recognize how the two terms that are here in the middle, they are like terms, even though they are written in different order. So remember, we have an implied coefficient of 1, and if we combine them, we will have a 2, which is what we have here, 2xy. And so from a polynomial with 4 terms, it reduces into a polynomial with 3 terms, which we call a trinomial. Now for the next expansion of x plus y, it will be raised to the power 3, but we still have the same binomial, x plus y. But now the exponent of a 3, it implies that we have x plus y times x plus y times x plus y. And so from the first two binomials here, x plus y times x plus y, we could use the same answer that we have here, the one that came from x plus y squared. And so with that, we will have x squared plus 2xy plus y squared times the other x plus y that we have here. So we will have to distribute first the x, so it will be x times x squared will be x cubed, then x times 2xy, so that will be 2x squared y, and then x times y squared, so that will be xy squared. Then we will do the same thing with the y, so it will be y times x squared will be x y squared. Then we will have y times 2xy, so that will be, okay, I think I made a mistake here, so I'm gonna try this again. So if I multiply y times x squared, it will be here, x squared y. Yeah, that will be the right place. Then y times 2x, then we will have y squared, so that will be below this one. So 2xy squared. And then we will have y times y squared, so that will be plus y cubed. So if we add the terms, we will have x to the third power, that's here. And then from this 2, adding vertically, we will have 3 times x squared y. Then from xy squared plus 2xy squared, we will have 3xy squared, and then finally y cubed. So if we were to continue doing the problems, the expansions in that form, we will get to do not more multiplications, but each multiplication will have more steps. So the process will become lengthy and, of course, kind of tedious. So we do have several ways, not several, a few ways that we could shorten that time. But before I teach you that, I just want to make sure that you understand how the exponent tells you how many times you will write the binomial and multiply by itself. So for x plus y to the power 4, I will write x plus y 4 times, multiply by itself. And so the result to that is what I'm about to highlight here. And as you can see, in this case, we have 1, 2, 3, 4, 5 terms, and the exponent was a 4. If we go back to the one with the exponent with a 3, if you count the terms, you will see that you have 1, 2, 3, 4. For example, if we look at y squared, the exponent is a 2, and the answer has 1, 2, 3, 3 terms. So we are going to be getting one more term than what the degree of the polynomial is, or one more term than the exponent that the binomial is being raised to. So just one more time, x plus y to the power 5, we will have x plus y times x plus y times x plus y times x plus y times x plus y. And so that is 5 times multiplied by itself. And the answer is down here. We have 1, 2, 3, 4, 5, 6 terms. And that will be the answer for the expansion of the binomial x plus y to the power 5. So to find those numbers, which are the ones that we do call binomial coefficients, and I'm going to just highlight here with this example what those will be. For example, here we have 5. That will be the coefficient. Here we have a 10. Here we have a 10. Here we have a 5. And for the first and last term, we do not have a number that we could see, but it's an invisible one or an implied one. So that will be also the coefficient. There are several observations you can make about these expansions. For example, 1, in each expansion, there are n plus 1 terms. So that's what I was saying about the degree of this polynomial, or the exponent for which we're raising the binomial, is a 5. And so because of that, we could say that n is equal to 5. And you could see that the number of terms will be n plus 1, which will be 6. And it is true for our example. We have 1, 2, 3, 4, 5, 6. 6 terms. Number 2, in each expansion, x and y have symmetrical roles. That is pretty easy to see. You notice how we have a 1 for the first coefficient and then a 1 for the last one. Similarly, we have a 5 for the second coefficient and a 5 for the second to last coefficient. And then in the middle, we have a 10 and a 10. And if we were to have an odd number of terms, we will have an extra one in the middle that wouldn't be, it would just be unique. It wouldn't have like a partner, a symmetrical partner. The powers of each of x decrease by 1. As you can see, we start with the power 5 for x, and then the next term has a power 4. I'm sorry about that. In each expansion, what we were saying about the decreases by 1 for the x. So you can see a 5, then a 4, then a 3, then a 2, then a 1, and then the last term you cannot see there's an x, but there is actually an x to the power 0. But as we mentioned previously, anything to the power 0 is equal to 1 except for 0. So if you had something 0 to the power 0, that wouldn't be equal to 1. That will simply be undefined. So we could see that x, the exponent for x decreasing, and then the powers of y, which is the second term of the binomial, you could see that those, we start with the first term has no y, so it's kind of like a similar case. We could assume that there is not an x but a y to the power 0 along with the x to the 5th. Then for the very next one, it will be to the power 1, then y to the power 2, then y to the power 3, then y to the power 4, and then finally y to the power 5. So I'm going to go ahead and highlight the exponents just to make sure you can visualize it. So we have y to the power 0, 1, 2, 3, 4, and then 5. And then finally, number 3, the sum of the powers of each term is equal to 5. So 5 is the big exponent, not the big exponent, well, the biggest exponent. So if we add the degrees of each variable, or add the exponents of each term, such as we have here with x to the 4th times y to the 1st, if you add 4 plus 1, you will get 5. And 5 happens to be the biggest exponent or the degree of the polynomial. If we check the next one, we have x to the 3rd and y squared. So 3 plus 2 is also equal to 5. And also 1 plus 4 1 plus 4 is equal to 5, and also here works 5 plus 0 is equal to 5, and of course it will also work for the very first one, which is 5 plus 0, and that will be 5. So that is true for every single term of the binomial expansion. And on the next slide, we have number 4, which is the coefficients increase. They go up and then decrease. They go down in value. And this is done in a symmetric pattern. So they will go up and then they will go down and they will be symmetrically. You could see this with the Pascal triangle once we get to it. The coefficients of a binomial expansion are called binomial coefficients. To find them, you can use the binomial theorem. And one of the things that perhaps you have not seen yet is the notation that it has like a little subscript of r, and then it has an n, also like a subscript but on the left side. And what that means is we could read it this way: n choose r. And so what it means is, for example, if I was to write 4 and 2, so that will be 4 choose 2. So it means from 4 items, choose 2 of them. So if we say 4 choose 0, that will be from 4 items, choose 0. And how many ways can you pick 0 items out of 4? Well, that will just be a 1. And that is the reason why the very first coefficient, binomial coefficient, is always going to be a 1. Now let's talk about the last one. So if we were to have 4 choose 4, and how many ways can you pick 4 items out of 4 without looking or randomly? It's only one way. So that is the reason why the last binomial coefficient will always be a 1. And this is true for any expansion, so any power that you're trying to say. So we can also generalize it to n choose n, that will be equal to 1. That will always be the last coefficient. And for the first one, we could generalize it by saying n choose 0. That will also be equal to 1. So we also can see what the 3 statements that were written on the previous slide. So how the power of x will be, will start with the same as the value for n, and then it will be decreasing by 1. And that's why you can see n minus 1. The next one will be n minus 2 until you get to 0 for x. And that will be the last term here. It's not written down, but I just wrote it. And then for the powers of y, we would start with the very first one being y to the power 0. And it's not written down here, but I'm going to write it. Y to the power 0. And then you could see how they will be increasing by 1 until they get to n. So we could see the 0, and then y to the power 1, and then the next one will be a 2, then a 3, then a 4, then a 5, and all the way until n. So I mean, n could be a 3, n could be a 2, n could be a 5, 100, whatever you want to make it. Okay, and now to find what each binomial coefficient will be, we will use the formula that you see written down here. And this is also the formula for combinations. And so combinations are one of the tools that we will use on the next section as well, which is probability. And what that tells us is that you're choosing random objects or values from a list. And in this case, with combination, the order doesn't matter. But that is something that we will go over more in detail in the next section. So the formula to find the combination of any two numbers will be using factorial, as you can see. So you take the biggest number, the total of items in your list. In this case, n is also representing the highest exponent or the degree of the polynomial. And so you will have n factorial in the numerator, and then you will have the smallest value, which is r, and that will be here in the denominator. And in addition to that, you will have, and of course, R also has factorial there. In addition to that, you will have the difference of n minus R to, and then factorial. Now, another way to write a combination that is not that NCR, like n chooses R, you could also use parentheses and write them the biggest number on top, the smaller or equal on the bottom vertically, kind of like a vector or a matrix. So let's go ahead and prove why using that formula. Let's see if what I wrote here is actually true. So if we take 4 choose 4 or 4 combination 4, based on the formula, we need 4 factorial on top for n. N is equal to 4. And then we need n minus r here on the bottom. N minus r will also just happen to be 4 minus 4 factorial. And then we also need the smallest or equal number, or the number on the bottom, to be in the denominator, but with a factorial as well. So for factorial, I will just I'm just gonna leave it written down that way for factorial, and then I'm gonna take care of what's inside the parentheses. So 4 minus 4 is 0, so we have 0 factorial times 4 factorial. So now you could see how 4 factorial times divided by 4 factorial is going to cancel out because they equal to 1. And even if you were to put it in the calculator, get the expansions, you will have 24 times 24. And even if you might be thinking that you can have a 0 in the denominator, remember by definition, 0 factorial is equal to 1. So now we have 1 over 1 because 0 factorial is also 1, and so that is equal to 1. The next one, I'm just going to leave it there. You could prove that one yourselves. Or maybe you will have a question like that on your homework, but they're pretty simple. You will also obtain a 1. So let's get to other examples here. And we're going to be using the same formula, so I'm just going to write it here. We use the big number first as n, then c, then r. That would be the small or equal number to n. And the formula is n factorial divided by n minus r parentheses factorial times r factorial. So the very first one, we already have the substitution. You could see here how n is equal to 8 and r is equal to 2. So you could see 8 for n is right here, 8 factorial. And then, actually, I'm going to write they're kind of like skipping a step here. So this should be 8 factorial and then 8 minus 2 inside parentheses, then factorial, and then finally 2 times 2 factorial. So from the 8 minus 2, that's how they obtain the 6. Then you have 6 factorial there. And then, of course, for 2, which is the value for r, that will be here, 2 factorial. So what I'm going to do, I'm going to actually make more room. So I'm going to erase this formula, write it somewhere else. And I want you guys to remember what we did. Perhaps it was section 9.1 when we started talking about factorials. So one way to save us time and also maybe the battery of your calculator will be to do this by hand. So 8 factorial will be the product of all the numbers from 1 to 8. But we know that from 1 to 6, that is equivalent to 6 factorial. So I can write 6 factorial times 7 times 8 in place of 8 factorial. From here, I could write 6 factorial on the bottom. And the reason we want to do that is so that we can cancel the 6 factorial from the top with the 6 factorial of the bottom. And then we have 2 factorial, which is just 2 times 1, which is 2. So right here, 6 factorial over 6 factorial is equal to 1. 7 times 8 is equal to 56. And then we have a 2 on the bottom. So 56 divided by 2 will be 28. Yes, 28. And so that will be the answer. So if we turn this into a question, in how many ways could you choose 2 items out of 8? It will be in 28 different ways. So let's do the next problem. Remember that is the same notation. And we will have 10 factorial because that is n over n minus, I'm going to write the formula here. Actually, I will write it here. It will be n factorial over n minus r factorial. This definitely is one of those formulas you want to keep on your formula sheet. And this is the combination of n choose r. So if we say that n is equal to 10 and 3 is equal to r, then we will have 10 factorial and then 10 minus 3 factorial and then times 3 factorial. 10 factorial over 7 factorial because that is 10 minus 3. Remember, you got to do that before the factorial and then 3 factorial. So at this point, you pick the biggest number with a factorial from the denominator, which is 7, and then that's how you are going to write 10 factorial. So you will use 7 factorial because they do have the same numbers, 7 times 6 times 5 times 4 times 3 times 2 times 1, but then we still need to multiply times 8 times 9 times 10 to have 10 factorial. Denominator will be 7 factorial times 3 factorial, and I'm just going to go ahead and calculate the factorial for 3, so that will be 3 times 2 times 1, so that is 6. So now numerator will be the product of 8 times 9, which is 72, times 10, which is 720. And it will be 720 divided by 6. And I believe this is equal to 120. So if we rephrase the question, 10 choose 3. And how many ways can we choose 3 items out of 3? Without considering order, it will be a total of 120 different types. If we were to consider the order of the terms as different ways to choose them, then we will have way more, but that will be a topic for next section, and those are called permutations. So the next one, similar to the examples that I gave you on the previous slide, we have 7 choose 0. So we have that n is 7. And then r is equal to 0. So following the formula, n, so 7 factorial on top. Bottom, we need n minus r, so that's 7 minus 0. Inside the parentheses, then factorial. And then we have times 0 factorial. So from here, we will have 7 factorial over 7 factorial times 0 factorial. And 7 factorial divided by 7 factorial is equal to 1. So we say they cancel, but they're not disappearing. They're still a 1. And then for the denominator, by definition, 0 factorial is equal to 1. So if we have 1 over 1, it's just 1. And the final one from this slide will be 8 factorial over 8 minus 8 factorial. And this is because n is 8, but so is r. And then we are also missing the 8 factorial. So in this case, we have 8 factorial in top and bottom, so it's equal to 1. And then from here, we will have 0 factorial because 8 minus 8 is 0. So this is 1 over 1, which is 1. And that was the same thing I was telling you on the previous slide. So our first and last binomial coefficient for any binomial expansion will always equal to 1. So to show the symmetric property of binomial coefficients, we could consider that whenever r does not equal to 0 and is not equal to n, remember we already proved when they're equal and when r is 0 with the previous two, that a choose 8. So when n is equal to r and also when r is 0, so in this case. So for those two, we got a result of 1. So obviously those two will be symmetrical. So now we're taking those two out, and there is a pattern for evaluating binomial coefficients that works because there will always be factorial terms that divide out from the expression. And so with the expression that we have here, I'm going to write it on the left side by using the formula. So this will be 8 factorial over 8 minus 2 parentheses factorial times 2 factorial. And so that will be equal to 8 factorial over 6 factorial times 2 factorial. And so remember that the long way to reduce this will be to, instead of writing 8 factorial, will be 6 factorial times 7 times 8 over 6 factorial times 2 factorial. And so that will give us 7 times 8, or 8 times 7, such as we have there. And instead of 2 factorial, it's 2 times 1. So we have that. And for example, if we were to calculate, let's say, the difference between 8 and 2, 8 minus 2 is 6, so I'm going to try 8 choose 6. So that would be 8 factorial over 8 minus 6 factorial times 6 factorial. So let's see if this works. So for 8 factorial, instead of that, I'm going to write down, well, let's just keep it like that for now, 8 factorial. And here I'm going to have 8 minus 6 is equal to 2. So 2 factorial times 6 factorial. And if you notice, it's starting to look a lot like this one here, because we're, instead of 8 factorial, I'm going to use 6 factorial and then times 7 times 8. And for the bottom, instead of 2 factorial, I'm just going to have 2 times 1 and then 6 factorial. I'm going to put it at the beginning. So we have again 6 factorial over 6 factorial, and we have 7 times 8 on the numerator, 2 times 1 for the denominator. So that could show you that symmetric property, because for both of those, the answer will be 56 divided by 2, which is 28. And so that is true in general terms. For n choose r, it will be the exact same number. In our case, we use the numbers 8 choose 2. It was equal to 8 choose the difference of 8 minus 2 is 6, so 8 choose 6. So those two are both equal to 28, and that shows the symmetric property of binomial coefficients. Now let's move on to an easier thing, and this is called the Pascal's triangle. And it is named after the French mathematician who invented or discovered, or in fact, it is said that people in China had a version of it that it was very similar, so I don't know, maybe he copied it off of them, but it is named after him. And I believe in your textbook, you can see the copy of the Chinese version of the Pascal's triangle, which is actually dated to centuries before the years 1623 to 1662. So there are other things that he discovered in, I believe it's physics, Pascal's law, or chemistry, I'm not sure, but it is, and it has something to do with gases. So what the way this triangle works is you have sort of like a pyramid or triangular shape, and at the top of the triangle you will have the coefficient of 1, which you could see here. And at the beginning and the end of each row or layer of the triangle or pyramid, you will have ones on the left and on the right side. So at the beginning and at the end. And we could see that for every row. 1 at the beginning, 1 at the end for every single row. So the way you find your numbers that for the of course the first and second row will just be 1 and then 1 1. So for the third row, what we're going to do is add the two numbers that I'm circling. So it will be 1 plus 1, and that gives me 2. Now if you recall the coefficients for x plus y squared, they were 1 x squared plus 2xy plus 1 y squared. So the coefficients, they happen to match the numbers for that row in Pascal's triangle. So we have 1 1 at the beginning and at the end, and then we do have a 2 in the middle. Now for the next row, the way we obtain the 3 in the other 3 is by adding 1 plus 2. 1 plus 2 will give us 3, and that's how we get that number there. Also, if we add 2 plus 1, we will also get 3. So if we go back to what we did on the previous objective, x plus y to the third power was equal to 1x cubed plus 3x squared. Remember how we decrease x by 1 and then we increase y. The first one was y to the 0, so the second term will have y to the first power. Then our coefficient is also 3, just like Pascal's triangle is showing us. And then it will be x to the first power and then y squared. And for the very last term, it will be 1 y to the third power. So the Pascal's triangle is a lot easier to compute, and I mean you could also use your notes if you're doing expansions. Let's say the very last row here, it will cover the coefficients for the expansion x plus y or any other binomial to the power 7. Yes. So just to, for fun, I guess, let's just add the numbers here. 1 plus 3, and we get 4. Then 3 plus 3, we get 6. And then 3 plus 1, 4. And so that's how you can construct your own Pascal's triangle. And of course, you do as many rows as you wish or as you need. And I'm just going to let's do the last rows just to So that you know that it does work for all. So if you add 1 plus 6 here, it will be 7. Then if you were to add 6 plus 5, it will give you 21. Similarly, 15 plus 20, it gives you 35. And then 20 plus 15, it gives you 35 again, so symmetrical. And 15 plus 6, we get 21. 6 plus 1, we get 7. And then remember, last element for that row will always be 1. So the first and the last numbers in each row are always equal to 1. So in this slide, you could see the same coefficients as the previous one. You could see how we have ones for the first and the last element of each row. So in this case, the coefficients for each polynomial or binomial expansion. So you could see that similar, well, exactly the same as the previous slide, just that only had the numbers. And then the other numbers, they also correspond to the ones that we went over before. So moving on, we have that the top row, as you can see here, the top row of the pyramid or the triangle, it is a 1 because it is x plus y to the power 0, which is equal to 1. And that is considered the 0th row, not the first row. The first row is actually gonna be this one, the one that has the exponent of 1. So similarly, the next row is called the first row because it has the exponent of 1. So we could say that the second row the coefficients of the second row will correspond to the binomial expansion of x plus y to the power 2. So in general, the number of row, in this case nth row, is in general terms that will correspond to the exponent that you are given here. So if we're talking about the 100th row, that row will correspond to the binomial coefficients of x plus y to the power 100. So to find the binomial coefficients of this problem, we use the 7th row, which was the last one that we had here. So I'm going to continue from here. So we're going to find x plus y to the power 8. And I don't think that's the full question. The question is just to find the exponents. So let's use the other one. Oh, I don't have room there. So let's just do it here. So the very first one, if we add 1, well, actually we have to start with a 1. The next coefficient is going to come from adding 1 plus 7, and that will give me 8. Then the next coefficient will be from adding 7 plus 21, and that will give me 28. Then we will add 21 plus 35, and that will give me 56. Then we will add 35 plus 35, and that will give me 70. Then 35 plus 21, and that will be equal to 56. Then we will add 21 plus 7, and that will be equal to 28. And we'll add 7 plus 1, which is 8. And then finally, remember how the last number will always be a 1. The first and the last are always 1s. So those numbers that you see there are the same that you could see here. And in fact, I left the solution here, so I could have done it here. 1 plus 7, then 7 plus 21, you get 28, and so on. So we do have the same numbers. And notice how here we have an odd number of terms. So, and it's because n is equal to 8, so the number of terms is always n plus 1, which will be 9. And so in this case, the term in the middle is 70, but every other terms, for example, the first and the last one, they are symmetric with each other. So for example, the 1 with the 1, and then we have the 8 with the 8, the 28 with the 28, and then the 56 with the 56. So you could see the symmetry going on there. So if we were asked to find the expansion, and I just want to do it because you will have questions like this on your homework, even though we're not asked to do it, let's just go ahead and write it down here. So we're going to have, for the very first term, we're going to have x to the power 8, and then we will have y to the power 0. Then we will have, for x, we will decrease the exponent by 1, so it will be x to the power 7, and then y to the power 1. Then we will have x to the power 6. It will decrease by 1, and the exponent of y will increase by 1, so it will be y to the second. Then we will have 56, x to the power 5, and then y to the power 3. Remember that at any time, if you're not sure if you have the correct exponents, you can add the exponents, and the addition per term should be equal to the number here, to n. So it will be equal to 8. So for example, we add 6 plus 2 is 8. If we add 5 plus 3 is also 8. Then the next term, for which the binomial coefficient is a 70, we're going to have x to the power 4. We decrease by 1. And then y to the power 4 because we increase by 1. So one goes down, the other one goes up, but the addition of those exponents at any single time should be equal to 8. The next term will have x to the power 3 and y to the power 5. And the next term will have x to the power 2, y to the power 6, and then 8, x to the power 1, and y to the power 7. And lastly, we will have 1x to the power 0, and then y to the power 8. However, I don't expect WebAssign asking you to leave the y to the power 0 or the x to the power 0 in your answer. They might perhaps even count it wrong, so just don't do it. The only reason I'm writing it is so that you can visualize how you start from 0 and work your way up to 8, or you go from 8 and decrease all the way to 0. So with example 4, when you write the coefficients for a binomial that is raised to a power, you are expanding the binomial. I think it's very clear what we're doing now. And the formula for binomial coefficients, the one that says n factorial over n minus r factorial times r factorial, for that formula, we already saw how we can get the same coefficients that come from the Pascal's triangle. So it's a lot easier if you already have Pascal's triangle, as we can see here on the next example. And I mean, this one is just way too easy because it's to the power 3. So let's make it a little more challenging and do something like x plus 1 to the power 4. So in this case, I'm going to write my coefficients. They're going to be 1. The next one, remember, you add the previous row coefficient. So 1 plus 3 is 4. Then the next one will be 3 plus 3, which is 6. And then the next one will be 3 plus 1, which is 4. And then the last one must be a 1. So we're going to start with x to the power 4, y to the power 0. Then we're going to have x to the power 3, y to the power 1. Then we will have x to the power 2, y to the power 2, then we will have x to the power 1, y to the power 3, and then finally x to the power 0, y to the power 4. Now what would happen if we had, oh, and I'm so sorry, but this is completely wrong because it was x plus 1, not x plus y. So I'm going to go ahead and change this y. I cannot do it, so I'm just going to have to write over it. It's just a 1. Instead of the letter y is a number 1. And so because it is a 1, it doesn't matter to what power we're raising the number 1, it will always be 1. So to give the final answer to this question, it will be x to the 4 times 1. Then we have 4x cubed times 1, 6x squared times 1. And then we will have 4x times 1, because 1 to the third power is still 1. And then we will have just 1 times 1 times 1. So it's just 1. And yeah, that is the answer. So since we have this example here, so let's see what would happen if that number was not a 1 and instead it was, let's say, a 2. So if we had x plus 2 to the power 4. So this will be 1 x to the 4 and then 2 to the power 0. Plus, we already know the next binomial coefficient is 4, so 4 x to the third power and then 2 to the power 1. Our next coefficient is 6, and then x decreases 1 on the exponent, so x squared, and then the number 2 to the power 2. And then we have next binomial coefficient is a 4, x to the power 1, and then 2 to the power 3. And the last term will have 1 for the binomial coefficient, x to the power 0, and then 2 to the power 4. Okay, so I'm going to simplify it. So for the first term, we're going to have x to the 4th power by itself, because 2 to the 0 power is a 1, so it doesn't, we don't need to write for x to the power 4 times 1. It's unnecessary. So next one, we have 4 times x cubed, but then we have here 2 to the power 1. So this will be 4 times 2 times x cubed. The very next term is going to be 6. And if I calculate this, 2 squared is going to be 4. So it's going to be 6 times 4 and then x squared. For the next one, we will have 4 for the binomial coefficient. In fact, I'm going to highlight my binomial coefficients so that you don't get them confused with the powers of 2. So it will be 4, and then 2 to the power 3, that is actually 8. So we're still multiplying that times the binomial coefficient, and then x to the first power. Then we have a 1 for the binomial coefficient, and we also have a 1 for the x to the 0, and then 2 to the power 4 is actually 16. So to write the final answer to this question, I'm actually going to make more room. So that will be That would be x to the 4. And then we will multiply here 4 times 2. So that will give me 8 x cubed. Then we will have 6 times 4. So that will be 24 x squared. Then we will have 4 times 8, which will be 32 x. And then finally we will have 1 times 16, which is 16. So that will be the final solution or final answer to that question. And the question was x plus 2 to the power 4. So it wasn't x plus y, it was x plus 2, and that's why we had 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. To expand binomials representing differences rather than sums, we are going to alternate the signs, but of course it's very important to note what the first sign will be. In this case, since x is the first term inside the binomial and x is positive, we will always start with positive x cubed, as you could see here on the answer. But I want to work out the problem first. So that will be 1x cubed. And that's, again, I repeat, because the sign for x is positive. Then you could see how the signs get alternated, negative, and then positive, and then negative again. Similarly with x minus 1 to the power 4, we start with a positive sign because x happens to be positive. So that will be positive x to the 4th. Then we go to a negative sign, then positive sign, and then a negative sign, and then positive sign. And notice how our binomial coefficients for the first one are 1, and also for the second one, and for the first and for the last, they're ones. And for x minus 1 to the power 4, first binomial coefficient is a 1, and last one is also a 1. So if we use the numbers from Pascal's triangle, or if you actually do every single combination, and I'm actually going to write here, you could see the numbers from Pascal's triangle. So for the third row, the numbers happen to be 1, 3, 3, and 1. And for the fourth row, they happen to be 1, 4, 6, 4, and 1. And again, we're alternating signs because we have a negative 1 here. But let's see where that is coming from. So for the very first one, the coefficient, the binomial coefficient, could be 3. You choose 0. And for the terms, it will be x to the power 3, and then the number negative 1 to the power 0. Then we will have the coefficient, the binomial coefficient will be 3, choose 1. That's where this number 3 comes from. And then we will have x squared, and then the number negative 1 to the power 1. Then we will have 3, choose 2. And we will have x to the power 3, and then negative 1 to the power, no, actually it should be x to the power 1, because we decreased that, and negative 1 to the power 2. And I don't have room to write the other one, so I'm going to have to use the space above. In fact, I'm just going to write it all again. So we said it was going to be 3 combination 0, x to the power 3, and then negative 1 to the power 0. Then we have 3 combination 1, x to the power 2, negative 1 to the power 1. Then 3 choose 2, x to the power 1, negative 1 to the power 2. And then we will have 3 choose 3, and for that will be x to the power 0 times negative 1 to the power 3. So from here we get a 1, and from here we also get a 1, whether the number being raised to the power 0 is negative, as long as it's surrounded with parentheses, it's going to be positive 1. So it will be 1 times x to the third power. The next term, the binomial coefficient, comes from here, and that will be 3. And then we will have x squared, and then negative 1 to the power 1, that will be equal to 1. To negative 1, actually, negative. Then for the next binomial coefficient, will be equal to 3 as well. And we will have x to the power 1. And then for negative 1 squared, it will be negative 1 times negative 1, which will be positive 1. And then for the final term, we will get the binomial coefficient from here, which is equal to 1. And then x to the power 0 is a 1. And then negative 1 to the power 3 is negative 1 times negative 1 times negative 1, so it will be negative 1. So finally, if we multiply, like in this case, 3 times negative 1, that's how we get this negative 3. And if we multiply positive 3 times positive 1, we get this positive 3. And finally, if we multiply 1 times negative 1, we get negative 1. And so that is another way. Of course, this works if you were, for example, I'm going to do one more. If we had, let's say, 2x minus, let's say, 3. And we're going to raise this to the power 3. Or let's put a 4 so we don't get confused with the exponent. In fact, let's make it more complicated and put 4y. So we're going to have 2x minus 4y to the power 3. So the very first binomial coefficient we already know is a 1. Then we're going to take 2x and raise that to the power 3, because that is what the highest exponent will be. Then we will take the negative 4y and raise it to the power 0. Then we get our next binomial coefficient, which we know is a 3. And then we take the first term from here, which is 2x, and that will be raised to the power 2. Then we take negative 4y, and that will be raised to the power 1. Then we will have plus 3 and 2x to the power 1 times negative 4y to the power 2. And then finally, we will have plus the binomial coefficient, which is a 1. And then we will have 2x to the power 0. And then finally, negative 4y to the power 4. So let's go ahead and reduce this. So it will be equal to 1 times, from 2x to the third power, I have to raise 2 to the third power, which is 8, because 2 times 2 times 2. And then x to the third power is just x cubed. For y, it's easier, because it's just raised to the power 0, so that would be equal to 1. Next binomial coefficient is a 3. For this part, 2x squared is going to be 4x squared. Also, the coefficient gets raised to that power. And then we have negative 4y to the power 1, so it's just negative 4y. Then we will have the next binomial coefficient is also a 3. We will have 2x, and then we will have negative 4y squared. So in this case, we have to square the negative 4, and that will give us a positive 16, and then y squared. And then for our last term, it's going to be the binomial coefficient is a 1. And then we have 2x to the power 0, so that's a 1. And then negative 4. And, oh, I made a mistake. That should not be a 4. That should be a 3, because that's what the binomial expansion is telling us to do. So this should be a 3. So negative 4 to the power 3 is like negative 4 times negative 4. So this is what I'm doing. Negative 4y cubed. So it will be negative 4 times negative 4 times negative 4. And then y to the power third. And so this will be equal to negative 64y to the power third. So now we're going to simplify by multiplying our coefficients. So 1 times 8 times 1 is equal to 8. And for our variables, we have x cubed. Then 3 times 4 is 12, times negative 4 is negative 48, x squared y. The next one will be 3 times 2, which is 6. And then 6 times 16, that will be 96 xy squared. And then for our last term, 1 times negative 64. And so that will be minus 64 y to the third power. And that will be the final solution.